So how we can still understand, or we still know that respiration is primarily controlled by two regions within the brainstem. What we see is our understanding of what each of these regions does has changed slightly over the years and is continuing to change. So we know that we have a region within the pons referred to as the pontine respiratory group, and then we have this larger, more active region referenced as the medullary rhythmicity center. Now, in the last edition of the textbook, we talked about this being the dorsal respiratory, or we talked about it as being the inspiratory area and the expiratory area. Now we refer to those areas as the dorsal respiratory group and the ventral respiratory group. Now, when these guys are functioning, in particular the dorsal respiratory group, it's going to send signals to your intercostals and to your diaphragm to set the basic rhythm of respiration. This basic rhythm of respiration is thought to be most influenced by the Prebutzinger complex. This area here is filled with autorhythmic cells. These autorhythmic pacemaker cells, similar to the heart, that set this automatic firing of action potentials to set the basic rhythm of respiration. Now, if we take a closer look at it, what we see is our dorsal respiratory group, which used to be the inspiratory area. Is going to have a repeating on-off activity. It's going to fire for about 2 seconds, and when it fires, the diaphragm contracts and we inhale. Then it's going to stop firing for about 3 seconds, everything relaxes, and we undergo our passive exhalation. Under normal resting activities, this is normally what's happening. Now, when we need to make modifications, then we rely on the ventral respiratory group. The ventral respiratory group is active during forced or inhalation and exhalation. So during forceful breathing, the ventral respiratory group is activated. So here we see a good reason why we changed the names from inspiratory area and expiratory area, because the ventral respiratory group, which used to be the expiratory area, has activities for both inhalation and exhalation. So the ventral respiratory group is going to be used during forced inhalation, where it activates additional neurons to your sternocleidomastoids, your pecs, etc., to get a more forced inhalation. And then it also will become activated to stimulate your internal obliques and diaphragm during forced exhalation. So this would be a good reason why we are renaming those groups. Okay. Now, within the pontine respiratory group, this is something, it seems to me, that we've kind of lost a little bit of understanding. The primary area within the pontine respiratory group, what we used to refer to as the pneumotaxic area, is thought to transition the changes between inspiration and expiration, but it's something we're still not quite clear on. Now, as far as how we regulate respiration, we can do so in 2 ways. Now, number one, you very uniquely have conscious control over respiration. You can choose to hold your breath, you can choose to take a deep breath, or you can choose to blow out a candle. This conscious control of respiration is quite unique for such a vital physiological activity. But because it's vital, it will always be overridden by visceral reflexes. So a lack of oxygen will always force you to breathe. This is demonstrated with anybody who's ever drowned. Okay? When you drown, you always end up with water in your lungs. Reason being is eventually your brain overrides your stimulus to hold your breath, forcing you to inhale even if air is not available. So these cortical influences, although you have conscious control over them, they will always be overridden by your ultimate need for oxygen, forcing you to breathe even when breathing is not capable. Now that, of course, is not what's going to get the job done, because I don't know about you, but when I start thinking about breathing all of a sudden becomes kind of complicated and weird. I'd prefer to just leave it up to my body to decide when I need to breathe more and breathe less. And that's primarily done via the chemical regulation of respiration, which is accomplished through your chemoreceptors. Chemoreceptors monitor the chemical characteristics of your blood. In particular, they monitor changes in hydrogen ion concentration, PCO2, and then PO2. Okay. Now, although they monitor all three, they're definitely by far more sensitive to changes in pH. Sorry about that, folks. Okay. Now, you have two sets of chemoreceptors. You have your central chemoreceptors, which are within the medulla oblongata. And these guys are monitoring the chemical characteristics of your CSF. Okay. Your peripheral chemoreceptors, on the other hand, are monitoring your plasma. Now, of these two, central chemoreceptors are by far more sensitive, which makes sense to me because what do we need to maintain more closely? Our cerebrospinal fluid and the physiology of our brain, or our blood? If our brain ain't working, it don't matter what our blood is doing. So central chemoreceptors by far are more sensitive and more active in controlling the physiology of our breathing. Okay. Now, how do they work? Well, if you have a disruption in homeostasis, in this case, our arterial PCO2 is going to increase. Excuse me. I was looking for whether we were increasing or decreasing here. I couldn't find it. Now, keep in mind, CO2 being a lipid-soluble substance is easily going to diffuse into the blood, which means if our PCO2 in the blood is increasing, then, and I've lost my pen again. Hold on, let me get my pen back. So again, if our arterial PCO2 is increasing, then our CSF PCO2 is going up. And remember, if PCO2 is going up, then our hydrogen ion concentration is going up, and our pH inversely is going down. This is first and foremost detected by our central chemoreceptors, although it's probably also activating our peripheral, but remember the central are the keys. This detection in the central chemoreceptors is relayed to the control center within the medulla oblongata. This increase in CO2 tells us, oh, we need to breathe faster, we need to breathe harder to get rid of this extra CO2. So we are going to stimulate the muscles of inhalation to breathe more frequently, ultimately leading to hyperventilation. As we hyperventilate, we get rid of our excess CO2, and this causes our pH to rise, and we return to normal. Now, just like in the cardiovascular system, we could also see an impact on proprioceptors. Proprioceptors monitor joint position, and they can increase the respiratory rate at the onset of physical activity. This is why no matter how athletic you are, when you climb several flights of stairs, your respiratory rate is going to go up. And this is because your proprioceptors are signaling the increased activity, and they're saying, hey, I'm exercising. She's going to need more oxygen here in a second. Let's get things going. Okay. You also have the Herring-Bauer or inflation reflex. This forces exhalation in order to prevent damage to your lungs due to overinflation. We certainly don't want our lungs popping like a balloon. And last but not least, there are a variety of additional reflexes that can affect respiration. Emotions can do it, blood pressure, temperature, pain, stretching of the anal sphincter, irritation of the respiratory mucosa, and can all have an influence on your respiratory rate. This nice little chart here is in your book. been converted to, let me see if I can find the table number. I like this diagram a little better for some reason, but in your book they converted it to a table, and it is table 23.3. But it shows you a nice graph on one side what increases, on the other side what decreases, giving you a nice overview of what's happening for the stimuli that affect positively and negatively affect respiration. Bringing us to some final questions to see where we are at. So the medullary rhythmicity center, in the medullary rhythmicity center, the dorsal respiratory group establishes the basic rhythm of quiet respiration while ventral respiratory groups remain inactive. Well, this is during quiet breathing. In quiet breathing, it is the dorsal that is activated. Remember, the dorsal respiratory group used to be referred to as our inspiratory area, and it's the primary one involved in everyday resting breathing. So let's see how well you understood the concept of CO2 and pH. Well, remember what I said. CO2 equals acid. Well, if our CO2 levels are increasing, that means we're making more acid, and if we're making more acid, our pH should be going down. Because remember, low pH equals acid. So you arrive late to class to find out there is an exam that you forgot to study for. You begin to hyperventilate. As a result, your blood pH ... Well, remember, hyperventilation means you're breathing faster. If you're breathing faster, then your CO2 levels are decreasing. If our CO2 levels that decrease, then the amount of acid in our blood is going to go down. If the amount of acid in our blood goes down, then pH should go up. Oops. That is obviously wrong, so when I reformatted this diagram, hyperventilating decreases CO2, decreases acid, and pH will actually increase, so ignore that. See, teachers make mistakes sometimes. But pH will increase. Sorry about that, folks. Finally, the last little bit of the respiratory system is going to be independent study. I do want you to read over the effects of smoking on the respiratory system and aging on the respiratory system. But other than that, that is it for your lecture, and I will see you back here for chapter 26.